as we approach a complex subject matter like the emergence of life, we are immediately faced with a hurdle, a conceptual concept that is really hard to get past because it's something we don't think about much in our daily lives. And that hurdle has to do with the concept of scale. How large or how small is something? And so the way that we want to approach scale in the emergence of life is to think about the dimensions of two very important properties. One of them is size, and one of them is time. So the properties of size we put into a category we call spatial. And so spatial dimensions, how large or how small is something. The spatial parameters are very important when we think about scale. The other concept of scale is time. And we use the word temporal for time, so temporal dimensions. So what we want to do now is, how do we approach extremely broad scales of spatial and temporal dimensions, of space, size, length, versus how long or how short an amount of time something takes to actually function and come to its completion or fruition. So the way we do this in the emergence of life is that we have to recognize that our spatial and temporal frameworks are incredibly large. In our everyday life, we're used to seeing things that, obviously, we use the human body as a good comparative standard. We think about, say, a tree being 3 times as large as someone, or we think about children being half or a third the size of an adult human being. So we always start by kind of comparing, and that comparison we just described, that's in this world of spatial dimensions and understanding how big or how small something is. But when we look at the emergence of life, we are talking about looking at dimensions of length scales of spatial dimensions that are incredibly small. The average diameter of a microorganism, especially bacteria, is about 1 micron. Well, 1 micron is 1/1,000,000th of a meter. And that 1 micron is one of the kind of functional units of spatial dimensions that we want to consistently be able to access and go to as we jump from 1/1,000,000th of a meter to talk about human beings that are 1.5 to 2 meters in size, to talking about meteor impact craters that are 50 kilometers in size, right? And each kilometer then, of course, is 1,000 meters. So how do we describe these kind of tremendous differences in size when we want to go from 1/1,000,000th or 1/1000,000th of something all the way up to 1,000 or 1,000,000 or 1,000,000,000 times larger? We have the same kind of problem with the temporal concept of dimension. We want to recognize and look at the lifetime of a human being, on average 60, 70, 80, 90 years in length, but we also want to think about the time frame over which it takes a cell to divide, which in many cases it can be within seconds, or some of the basic chemical reactions, like when we breathe in oxygen and then release CO2. Those dimensions of time are in a fraction, a tiny proportion of a second. Then we go to the age of the Earth, 4.7 billion years. That's a tremendous increase over 1 second of time. So these are enormous distances, if you will, of scale. So how do we go about doing that for both space and time? And the way we do that is, first of all, we consider a critical conceptual benchmark. We say to ourselves, is something 10 times larger or 10 times smaller? Is something 100 times larger or 100 times smaller? Is something 1,000,000 times larger or 1,000,000 times smaller? But that first functional unit of saying, is something 10 times larger or 10 times smaller? That is where we want to start with understanding how to look at the dimensions of time and space. And by centering it around that template of if something 10 times larger or 10 times smaller, we call the approach the powers of 10. If something's twice as large as something else, it catches our interest. But if something's 10 times larger than something else, it proves itself to be fundamentally important, fundamentally different, just because of the magnitude or size of that scale change. So the nice thing about the powers of 10 approach and centering the idea around 10 times larger, 10 times smaller to start with, is that then we can put the concept of describing length scales and time scales into a 10 by 10 by 10 basis. So we can say, is something 10 times larger? Is it 100 times larger? Is it 1,000 times larger? And if we go to the concept of something being 10 times larger, then if we put the framework of 10 into exponential notation, which goes to the point of saying that we put the number 10 and then we make a small exponent that tells us how many zeros come after that 10. Is it 10? Is it 100? Is it 1,000? 10 to the first is 10, 10 to the second is 100, and 10 to the third is 1,000. And by focusing on the exponent, instead of saying out all the zeros in terms of the number, like the word 1,000, then we can say that this microbial cell is 10 to the third larger than some of the molecules that make up the DNA of that microbial cell. Then we can just drop off the 10 part of the description and we can focus just on the exponent, which is 3. So if something is 1,000 times larger than something else, then we say that that object is 3 powers of 10 greater. So something that's 10 times larger is 1 power of 10. Something that's 100 times larger is 2 powers of 10, and so forth. And we go in the opposite direction. When something is 2 powers of 10 smaller than something else, that means it's 100 times smaller. So this powers of 10 conceptualization and framework is really powerful for us. And another phrase that we're going to be using throughout the Emergence of Life course is that we also say that 1 power of 10 is 1 order of magnitude. So something that's 10 times larger than something else is 1 power of 10 larger, and it can be described as 1 order of magnitude larger. Let's say that the average child is 1 meter in height, and that we want to understand then how that child fits into the framework of a kilometer, right? So there are 1,000 meters in a kilometer. And so if we say, well, that meter scale, let's say that they're standing next to the front range of a mountain, that's a kilometer in size, and there's a child that's 1 meter in height, then we would say that that mountain that the child is standing in front of, it's 3 powers of 10 larger than the child. It's 1,000 times larger than the child, and we can also say that it's 3 orders of magnitude larger than that child. And this concept of how to approach these immense diameters of scale, of time and space are what will give us the ability to communicate then about going from the evolution of early cells all the way up through fish, dinosaurs, and now eventually human beings.